So we haven't talked a lot about Ampere's law. If you remember, suppose I have a current that's into the page. You already know that the right-hand rule tells you that the magnetic field lines are going to circle around it clockwise if the current is into the screen. And Ampere's law tells you how to calculate that magnetic field. It says, well, if you're at radius r away, then B dot dl. B is a bunch of magnetic field vectors pointing like that around the wire. And so B dot dl is along this path, circular path around here. B is in the direction of dl, and so it's just B. And B is equal because this is the same distance everywhere. It's a circle centered on the wire. I enclosed is just the current. Mu 0 is a constant. B is independent of the angle here, so it comes out of the integral, and then, so it's just B times. You end up with the left-hand side as just being B times 2 pi r, the circumference. When you do the integral, B is a constant, and the integration of dl around a loop is just the length of the loop, so 2 pi r, the circumference, and that's mu 0 I, and that tells you what B is as a function of r. So that's what Ampere's law lets you do. If you can find a loop, Ampere's law says integrate B around a loop. When you do that, it's related to the current that goes through the loop. So what you need to do this easily, to make this easy to do, what you need to do is find a magnetic field that is equal at all points on the loop, same magnitude, and is either parallel, tangent to the loop, so B dot dl is just B times dl, or perpendicular, so B dot dl is 0. Having an angle that changes, I mean, that just complicates the integration. Having B dot dl, it's B times dl times the cosine of the angle between them. If that angle is changing around as you go around that loop, then you have a complicated problem. Here it is not. Here B and dl are in exactly the same direction, so the angle is 0, and the cosine of that angle is 1, and that doesn't change as you go around the loop. So it ended up just being B times the integral of dl around that loop, which was 2 pi r. So that's how we use Ampere's law for something that is a one-dimensional object. In other words, an infinitely long line of current. Single current, infinitely long. So here's a two-dimensional sheet. It's infinitely long, infinitely big, in fact, in the xy plane. They say it, they can't show it, but it goes on infinitely. Each of these lines of current, each of these wires in some sense, if it's made up of a bunch of wires, each of them is infinitely long along the y direction, and you have a stack of them along the x direction so that it spreads out to infinity along the x direction also. So it's a two-dimensional sheet of current, and so my question for you are we going to be able to find a loop where the magnetic field is either parallel to the loop, so cosine of theta in this dot product is 1, or perpendicular, so cosine of theta in that dot product is 0. So will ampere work, or are we going to have to use Biot-Savart's law and do an integration over this infinite sheet? So I forgot to tell you that you're running out of time, but you did. Sorry about that. So the main answer is yes, you can use Ampere's law. I think I'm going to. So my answer is yes, you can. But as far as you can use Ampere's law. But I think I had a question next about how you might use it. So here's a cross section of that same thing, where I have the x-axis to the right and z-axis downward, and so the y-axis is coming right at you. The current is coming right at you along the positive y direction in this picture I drew here. And so my question for you is the magnetic field above the sheet, in other words, z less than 0, that's the negative, above the sheet is up here. What direction does the magnetic field up there point? Due to an infinite line of, or infinite sheet of current, or it's an infinite line of a whole bunch of currents stacked together. So, taking into account all of the pieces, every single piece of the sheet of current, what's the direction of the field up above? So, main answer is to the left. So, what's the magnetic field look like around just this one right here? Well, this center one, magnetic field just due to this center one certainly circles around, and by right-hand rule, you're going to see, I think, your thumb points toward you that it circles counterclockwise because the current is going toward you. So if you're up here, the field due to that one that's right below it is to the left, so negative x direction. What about the field right there due to, let's go over 1, 2, 3, 4, due to this current? Well, a loop around this current piece right here that's circular, you can tell how great a circle that is going to have a magnetic field. Again, it's counterclockwise, but by the time you get over here, it points to the left and points down. And if you go 1, 2, 3, 4, if you go over here to the left 4 and draw an ampere loop to integrate around that one, then again, it's counterclockwise. They're all counterclockwise because of the right-hand rule and all the currents are toward you. And so over here, the magnetic field points in that direction. This is the closest, by the way, so I should probably make this one somewhat longer because this one in the center is closer, bigger magnetic field. In any case, every time I look over here and I find one that's to the left and down, there will be a wire over here that's to the left and up. So the symmetry of the problem, if you add all the pieces together, you'll end up with something that points to the left, up on top. What about down below? Well, counterclockwise. So that one looks like that. Counterclockwise for this one means this one looks like this. And for that one means that the one on the left produces a field that looks like this. The one on the right produces a field that looks like that. And the one in the center produces a field that's to the right. So to the right, down below, and to the left, up above, is the direction of the total magnetic field And that doesn't matter where I look up above. Wherever I look up above, there's going to be a magnetic field to the left. And wherever I look down below, there's going to be a magnetic field to the right. And so an Amperian loop that I can integrate around could be something like that, because up here, B is parallel to DL. And down here, B is parallel to DL. So again, the dot product just gives you B times DL. And when you integrate it, and it's constant across there, so when you integrate it, it's just B times the length. That's just B times that length. And over here, B is perpendicular to DL. As you go around the loop, DL would be vertical, and B is still horizontal. So B is perpendicular. So those pieces of the side pieces don't contribute. So you get a B times L up here, a B times L there, as the sole contribution on the left from that line integral around this loop. And on the right, I enclosed, and the amount of current enclosed just depends on the width of the loop. It just depends on the L that I chose for the width of the loop. And so the width of the loop will be on each side. So what can you say about farther away? Say I chose the same width loop, but I want points farther away. Well, the current enclosed is the same if it's the same width loop. B times DL is still B times this length, B times that length, that's the same. So for this infinite sheet of current, you have a magnetic field that points either to the left above or to the right below, and doesn't get smaller as you go farther away. Now, there really aren't infinite sheets of current, so, and I don't know of a common use for that kind of geometry, where you have a sheet of current that's really big. So I'm not sure how useful this is, other than it's an interesting situation that the magnetic field of this kind of thing doesn't depend on the distance from it. There's one other interesting use of Ampere's law, and I don't think I've said anything about it yet, and that is if you have a really long coil. If you have a really big coil, infinitely long coil, then you know that each piece, each loop of this coil produces its own magnetic field. All the loops inside, because they're all wound in the same direction and have current in the same direction. Currents going around and around this thing in the same direction. All of the magnetic fields inside the loop will point in the same direction. Outside the loop, they're going to point in all sorts of different directions, and you can check this if this is a very long coil, infinitely long, then the magnetic field outside is just going to cancel. There's not going to be a magnetic field outside the coil if it's an infinitely long coil. No magnetic field. And so what sort of loop? Let me cut this. Coil. If we look at a cross-section of the coil, there's going to be a bunch of wires on one side with the current coming out. On the other side, those same wires are going to loop around. The current's going to go into the page. And so Okay, what I just drew is going to have magnetic field down instead of up. I'm just going to draw it down. If that's an infinite coil, what sort of a loop might you use to use Ampere's law? And the answer would be a loop that looks like that. Because the top of the loop, the top part of the loop has B dot dl equal to 0, because B is perpendicular to dl. Same with the bottom. The right-hand side has no magnetic field, so that's 0. And the left-hand side has all the magnetic field, and it's parallel to dl. So B times that length is the only piece that's left out of B dot dl when you integrate around that whole loop. Just B times that length. And that's equal to the current enclosed, and the current enclosed is just the current times however many loops go through that length, the loop that's this tall. So an infinite coil is another situation where you can use Ampere's law to find the magnetic field. Of course, nobody ever makes an infinite coil either, but they do make long, thin coils, so it's a pretty good approximation. We use long, thin coils a lot. There's one other thing that you can do. You can make what is essentially an infinite coil by winding by putting a current through a coil that you've bent back and wrapped on itself. So if I had a coil like that, and I take the ends of that coil and I pin them together, I make a torus out of that coil. And that kind of a toroidal coil doesn't have an end. In fact, all of the magnetic field goes around inside, and none of it is outside. And so it's a lot like an infinite. Whenever you take something and bend it back on itself, you've produced something that doesn't have an end. So it's a lot like the infinite coil. So toroids are also a kind of coil that people use. And those are the main uses of Ampere's law. There's a line of current, so a straight wire, infinitely long. There's the infinite sheet, which is useful. And then there's the infinite coil, which can be wrapped around on itself in terms of a toroid. Those are all of the uses basically of Ampere's law in this form.